Okay? So the maximum kinetic energy of the electrons, what's the anomaly here in this particular experiment? It turns out that the maximum kinetic energy of the electrons that are ejected depend on the frequency but not of the intensity. So what's so anomalous about this observation is that, remember, in the wave model, what did we say the intensity was? A measure of, okay, intensity for one thing, intensity is energy, right? Transported per unit time, per unit time, per unit area, right? So energy per unit time is watts per unit area. That's joules per second, and area is square meters. Um, so you would think that the more intense you make the radiation, you're putting in more energy, you should be able to knock off more electrons and get them to move faster, right? But it turns out in some cases, if you are below a minimum frequency, that's called the threshold frequency, you can't get any electrons out regardless of how intense you make the radiation. So how could it be you're making the radiation give you as much energy as possible, but you can't knock out any of the electrons? Okay? But if you have the right frequency, if you're above this minimum frequency, it doesn't matter how weak the light is. The intensity doesn't matter. It doesn't affect what the maximum kinetic energy of the electrons is. Okay? So anyway, H times this threshold frequency here, nu naught, is now what we will call your work function. And we're going to understand later why it's called the work function. But what makes this anomalous is that instead of the kinetic energy of the electrons depending on intensity, it actually depends on the frequency. In fact, the higher the frequency, the higher the kinetic energy of the electrons. Okay? So if the frequency is higher than the threshold frequency, okay, you just simply get more electrons ejected at higher intensity. But the kinetic energy is not dependent on intensity. So for a particular frequency, let's say for a particular frequency you can get electrons to come off. Okay? It doesn't matter how intense you make the beam, okay? It doesn't matter how intense you make the light. The kinetic energy doesn't depend on the intensity. It only depends on the frequency. Okay? What intensity does is just gives you more electrons. So it increases the current through your circuit, but it increases the number of electrons ejected, but it does not affect the kinetic energy of the electrons. Okay? In fact, if you were to plot the kinetic energy versus frequency, this is what you'll find. The equation, okay, is given by this right here. Oops. Expression right here. So if you plot kinetic energy versus frequency, you're going to get a straight line. So there's a minimum frequency that you need to get electrons to eject. So let's call that nu naught. That's the threshold frequency. And you're going to get a straight line if you make a plot of kinetic energy max. Okay, I'm just going to start dropping the max. Okay, what I mean. So when I just write KE here, I mean the maximum. You're going to get a straight line. And so if you fit that those data points to a straight line, your data would have a slope of equal to h. Okay? And the y-intercept would be negative h nu naught. Okay? In fact, when kinetic energy is 0, what happens? What happens when Ke max is 0? When 0 is equal to h nu minus h nu naught, then nu is equal to nu naught, right? So your x-intercept right here, okay, at nu naught, kinetic energy max is 0. Below that, so this section right here that's not observable because this is the minimum energy right here, minimum frequency right there that you need to get electrons off your metal. And it turns out this slope of the line, you can see this is y equals mx plus b. See? So the slope of your line is h. Okay? Your x, this is your x-axis. So what kinetic energy is on your y-axis, and your y-intercept, that's your b, is negative h nu naught. Now, like I said, it's a straight line, and the slope turns out to be the same h, the same value that Planck got when he tried to fit the black body radiation. Same constant came up. Two completely different experiments. Same constant came up. Okay, that suggested that that h, Planck's constant, is in fact a universal constant. It's not just applicable to one particular situation. Okay, so the slope of the line that they got, they would get different plots for different metals. Okay, so depending on what the metal is, you have a different threshold frequency. But all of these lines are going to have the same slope. They all have the slope equal to h, and that value of h is the same. All right.
What did you say H mu naught stood for again? The work something?
It's called the work function. Okay, it's called the work function, and we represent that with the letter phi. Okay, so